So welcome all to week 5 tutorial for the course Essential Mathematics for Machine Learning. I am Pintu Kumar. I am a PhD scholar at IUR IIT Bombay. So the topics that we plan to cover, this week was sort of devoted to machine learning part. So I would like to talk about lot of things today. I'll talk about regression. I'll talk about logistic regression, which is indeed a classification technique. Okay, I'll talk about other things like bias and variance. Okay, so in this portion, I'll also talk about underfitting and overfitting and regularization and those things. Okay, and overfitting. Okay, so towards the end, if the time permits, I'll also talk something about gradient descent method, which was discussed in the lecture very briefly. Okay, and some variant of gradient descent techniques, and so that you know when to use what kind of gradient descent. Okay, and second thing that one more thing that I have planned that would be only if the time permits is maximum likelihood estimator, and what is the meaning of that. Okay, so this is the plan for today. At any point in the lecture, if you have any doubt or you want to ask anything, either you can type it in the chat box or you can just unmute yourself and speak. Okay, so this course is about essential mathematics for machine learning, but most of the part that we have covered till now is related to the mathematics part. Okay, so I would just take a few minutes, right? Okay, so if you look at the regime of hello. Okay, yeah. If you look at the regime of machine learning, then you can broadly divide it into three, four kind of tasks, but majorly two kind of tasks that are very like dominant today are regression and classification. Okay, so these are types of supervised machine learning. Okay, these are subsection of subpart of supervised machine learning, and so this is regression and classification. Okay. First of all, what do we mean by supervised machine learning? So supervised machine learning is where you have, so in machine learning what we do, we try to train a computer or we try to train a model to learn from certain set of examples that we have. Okay, so let's say when we were a child, we used to look at many things and our parents used to tell us that is a dog, that is a cat, and that's how we learned, right? So in a similar fashion, we try to give certain examples to a machine and we try to train them to learn what that particular thing is. Okay. So in supervised learning, we have data as well as its label. Okay, data plus whatever labels or value we want as an output. Okay, so we have some features and associated output. Okay, so so what kind of models we want? We want a model. If in future we input some random xi, then we should get the corresponding yi's. Okay, so if the difference between regression and classification is that in case of regression, the yi is a continuous value. Okay, and for your classification, your yi is a discrete value. Okay. So for example, if you look at, let's say, you want to predict the price of a house at some place based on its weight, locality, and those kind of things. If you look at this example, this is an example of a regression example because the price that you'll predict is continuous in nature. Okay, and for example, let's say if you have a bunch of images that contains dog images and cat images, and you want to train a model that can tell you whether that particular image is of a dog or a cat, then this kind of model is a classification model. Okay, so a very brief thing about this thing. Okay, so yeah, the question comes is what do you want to learn? Like told you that it will learn from example, but what do you want to learn? Okay. So if you look at some a classic example how your data set exists, let's say you will have some feature 1, okay, you will have some feature 2, let's say we have some 3 features, okay, okay, and you will have many data points having these features and let's say some value of y also, okay. So now let's say you have x1 which is let's say 2, 3, 4 and the value predicted is let's say 1. Let's say you have some x2 also, this is 5, 7, 8 and let's say this is 10 or something of this sort, okay. So now in practice, let's say if you look at a kid, the kids are quite curious when they are child. Also, they tend to repeatedly ask same question. For example, if you look at a small kid and you tell him that this is a crow, okay, the next day it is possible that the child will again ask you what is this. So it is possible that one example might not be sufficient for the child to learn that that particular thing is a crow, okay. So that same thing happens in machine learning also. Generally, the number of data points that we have is much larger than the number of features that we have, okay. So this is a general trend that we have, okay. So in such case the question is what do you want to learn, okay. So what we try to do is as this is a mathematics this is essential mathematics for machine learning, so I'll motivate it that way. So we want to learn a function f such that if we give some input to it, it will predict y, okay. Now a very easy example can be your function can be something of form ax plus b, where a and b have some value, for example 2x plus 3 or something like that. So in machine learning what actually you learn are the values of this a and b, okay. So you like first of all assume what sort of functions that you want to search for, okay. So what kind of function do you want to allow your algorithm to learn, and then based on that you decide upon these weights or the constants that you want to fix, okay. So this is the broad idea of how your machine learning algorithm works. So the answer to what do you want to learn is that you want to learn the weights or the parameters, okay. So parameters to what? Parameters to some function. For example, if you wanted a quadratic function, then your parameters would have been a, b and c, okay. So now let's look at this example, okay. So we have let's say a 2D plane, we have point 1 0 and 0 1. So the question is how many lines can you draw that passes through these 2 points, okay. So the answer is pretty simple, right, that there is only one line, straight line, that will pass through these 2 lines, okay. So this was quite simple, right. Now if you look at this particular example, the question is how many line passes through 0 1, 1 0 and 0 0. So the answer is that there is no line that would pass through, okay. So as I mentioned that we want to learn these kind of parameters, another important thing that you have to choose while formulating your machine learning model is you have to fix what kind of functions you want to allow, okay. For let's say I just wanted my functions to be linear, okay, that my function should be just straight lines, so that if I input some give it some x value, it should give me let's say this is ax1 plus a1x1 plus a2x2 plus b. So linear, even if it has 2 features, it is just a linear function, okay, with some bias term. This b is called bias, okay. Otherwise we would only have line passing through origin, okay. So we just allow all lines, okay. So to allow all lines we include the bias term also. Now there is no line that would pass through these 3 points exactly. Okay, so what is the idea? Idea is that we want an approximate line, okay, that minimizes the error. Error between what? So let's say you have f of x is equal to ax plus b, and you want to learn this a and b if you have a straight line in 2 dimension. Okay, now let's say you already had some values. Let's say for x you have some y. Let's say for 2 it's 4. Let's say for sorry, let's take this example only. So for example, you have for 1 it is 0, for 0 it is 1, and this shouldn't ideally be the case. So let's take this to be 0.1. Still the line won't pass, so let's take this 0.1 to be 0. Okay, now for this line you will have some a let's say tilde and b tilde. Based on that, if you calculate let's say y hat is equal to a tilde x plus b, you will obtain some values inputting x. Let's say this is something. Let's say this is y1 hat, this is y2 hat, this is y3 hat. Now if you take the error between this y and y hat, okay, what you want to do is you want to minimize this error. You want to find a line such that this error between this thing is minimized. So here you have this much error, here you have this much error, here you have this much error. So you want to find a line so that some of these errors should be minimum. Okay, so that is the whole idea behind linear regression. So linear regression is finding a linear curve fitting your data points. Okay. Okay, Kushal, can we get to this PCA part towards the end?
Yes, sir, no problem.
Okay. Okay, so first of all, why do we need linear regression? Okay, so first point is that this is quite simple, right? This is just a straight line that we are finding, and optimizing this also becomes very easy. So this is very simple but very powerful. Okay, how is it powerful? We will come to that point. Okay, second point is, as these are very simple functions, so this provide interpretation. So if when you will learn about deep learning models, you will come to know that those models are not interpretable. So you can't say why did you get this kind of prediction from your deep learning model, but here you can tell, somehow you can tell. Okay, so one point that is related to the first point, although we are using linear curves, but we can use them, we can use this linear regression technique to approximate even the non-linear curves. Okay, okay, so we will see how can we do that. Okay, so let's say you have some feature f1, f2, okay, and f3. Okay, and you have data points x1, x2, x3, and some points filled in this. Okay, now if you ideally had a linear function, then this would have been of form something like alpha 1 f1 plus alpha 2 f2 plus alpha 3 f3 plus some bias. Okay, so you would have approximated alpha 1, alpha 2, alpha 3, and some b, right? But let's say this data would have been from some domain. Let's say this is from biology or physics or from some social experiment, and you have some idea that we don't just want a linear function, but we want some more complicated polynomial functions. For example, you want something of sort, let's say alpha 1 f1 square plus alpha 2 f2 into f3, then we can have something like linear f1 plus alpha 4 f2 plus alpha 5 f3 plus some bias. You have some prerequisite idea that we want this kind of function. Okay, so then you need not like derive everything from the scratch for this kind of thing. What you can do is you can include some new features to your data set. What would be those new features? You can just include f1 square as another feature for your data set and f2.f3 as the second extra feature for your data set. Now, as you have scaled the features itself, now if you take a linear function of all these things, what you would be getting is you would be getting a non-linear sort of function, a polynomial function. Okay, so you can very much use your linear regression to approximate okay non-linear functions. Any doubt till this point? Any doubt before we move ahead? Okay, so yeah. So how do we, this plot I included, I just wanted to show you that if you are talking about linear regression, so how do you calculate the error? You calculate error between f of x and y, right? So for example, if you are for 0.6, this line here gives you f of x, right? So how do you calculate the error? You calculate the length of this line. Okay, calculate the length of this line. This line is perpendicular to your y-axis. Okay, there is another kind of algorithm that some of you might know, and it would come towards the end of this course, where you take rather than taking the distance perpendicular to y-axis, you take distance perpendicular to your this particular line itself. Okay, so this algorithm gives you something called as support vector meshing later on. I will come to it towards the end of the course. Okay, yeah. So this was the idea, okay, of linear regression. Now we have come up with an algorithm which is called linear regression for our machine to learn. Now what we'll try to do is we will analyze whether this machine learning algorithm is effective or not. Okay, so now let's say uh, we have uh, yeah, we have a data set of this type. Okay, so if you are able to visualize your data, anyone can say that this is sort of a parabolic data, right? And it is best to fit a second order polynomial to this kind of data set. But let's say somebody wants to fit a linear line to it. Somebody just want to fit a line to it. So maybe this can be the best predicted line. But if you look at the error, even for the best line, the error is very high. Okay, and this particular thing is not at all giving you an idea about how your data set looks. So this line is not at all a very good representation of your line that you are having. Okay, so in such situation, when the model that you have chosen is not a is uh, is an insufficient representation of actual data, in that case we say that our model is underfitting. Okay, so it is not capable enough to incline with the data set that we have. So this phenomena is known as underfitting. Okay, now the second situation that arises is, so one thing that you should not appreciate but keep in mind is that whenever we collect data in real life, those data points are prone to some errors. Okay, so those can be due to many reasons, that maybe you don't have many trained people to collect data, and you have sent someone who don't have expertise in that area to collect data, or you might have some faulty machines, or when you are feeding your data into your computer, that time you made some error. Okay, so there are many possible sources of error or noise in data. Okay, another source can be that you didn't consider all the factors that would have been necessary to reach to a conclusion. Okay, so because our data set is not very pure, it has some noise in it. So if you look at your training data, okay, I think most of you must by now must know that when you train a machine learning model, you have three kind of data, right? You have some training data, you have some testing data, and you have some validation data. Okay, so you use some part of it to train your model, and then you test on rest of them. Okay, so because you don't, what you want to do is, somebody is joining. Yeah. So because your data is prone to some noise, so it is possible that the distribution of your training data is not very much inclined with distribution of your testing data. Okay, so now if you have chosen a very high degree polynomial, okay, and you have fitted very well to your let's say data points, then there is a possible that you will make very large error on your testing data set. For example, we can have a very small example. Okay, let's say your data point looked something like this. Okay, so you took a very high degree polynomial and you fitted a line something like this. Okay, you fitted a very good line to it. Now let's say you come to know later that this particular point was a erroneous or a noisy point. Actually, this point should have been here. Okay, now if you look, because of just that point, if you again try to fit that polynomial, you will make a lot of error, okay, for prediction in this zone. Earlier, let's say if you had, I'll try to draw something similar. Okay, so this is this. Okay, now if you wanted to fit a line, then the best fit line would have been something like this. Okay, now even if your this point got removed and this point was added, then possibly your line would have moved from there to, let's say, something like here. Okay, this is the best possible thing that you could have got. So the error that you are making if you are using simpler function, if you have some noise in data, is very less as compared to when you are sort of taking your functions to be very complex. Okay, so this situation, when you choose your polynomial degree very high or your set of functions very complex, then your model tends to fit very well to training data. Okay, but perform poor on your testing data. So this kind of situation is known as overfitting. Okay, so what is overfitting? Overfitting is fitting very well to your training data but performing not that good on your testing data. Okay. Okay, so we will come to the solution. How can we avoid underfitting and overfitting? Actually, there is no solution. You just need to find something like Pareto optimal, or you have to pick a model complexity which is between your underfitting and overfitting. And yeah, that's what the solution is. But how can you know that? That we will come to. Okay. Now we will solve some problems related to linear regression. Now what I said is we want to minimize the error. Okay. Now you had some, if you remember, you had some feature f1, f2, f3, and you had some x1, x2, x3, and so on. Okay. Now if you write this matrix, write this feature set as a matrix, then you can obtain a feature matrix. Okay. So what, let's say its dimension is m cross n, then what is m? M is your number of data points, and n is your number of features. Now, as I mentioned earlier, like if you have your data sets, then your numeric example is actually very high as compared to number of features. Okay, so if you look at this system of equation that you're trying to solve, so as mentioned in the lecture, if you have, let's say, something like a1 x1 plus a2 x2 is equal to some y1, this is b1 x1 plus b2 x2 y2, and so on, let's say till zn x1 plus z1 x1 plus z2 x2 is equal to some y26. Okay, now if you have many equations and less number of variables, then what you land up at is you don't have any exact solution to this. Okay, so if you look at the example that we took few moments ago, this example where I asked you to fit a line passing through these 3 points. So I had more number of equations and less number of variables to satisfy. Here I had 3 equations and only 2 variables. Okay, so I was not able to find an exact solution. So in that case, we try to find an approximate solution which minimizes the error. What kind of error? That I already mentioned. So error of this sort. So which is fx minus yi second norm. Okay. So if you look at the solution which can minimize your error, that is given by A transpose A inverse A transpose B, where your B is your y vector that you can say over here, the y vector that you got. And if your data set is in form xi comma yi, then this is the y vector that you will get by writing y1, y2 and so on. Okay. So this is the least square solution. There are quite a few to derive this. There is a probabilistic approach using maximum likelihood estimator. There is a matrix theory approach by finding the minimum. One approach has been done by professor in the course also. You can have a look at it. I'll just refer to the formula straight away. Okay. Okay. So we'll sort of stop at this point and look at some of the examples that have been asked in assignment or similar questions. Okay, so we'll try to solve similar questions to what are in assignment. These are not exact same questions. Okay, so we'll try to solve them. Okay, so that you can get some help in that also. So yeah, this whole story begins with system of equation. So in this question, you are given a linear system of equation and you have been asked whether this system of equation will have unique solution for every choice of b1 and b2, or infinitely many solution, or solution won't exist, and those kind of things. Okay, so how do you do this kind of examples? We have discussed it earlier. What you need to do is you need to write the augmented matrix for this. Okay, so augmented matrix would be 1 2 2 b1 5 1 3 b2. What I did, I wrote just the coefficients from here in first row and coefficients from second equation in the second row. Okay, now what we will do is we will try to row reduce this thing. Okay, so what I can do is I can do r2 goes to r2 minus 5 times of r1, right? So this would become 1 0, this is 2, this would be minus 9, this is 2, this would be minus 7, and this would be b1, and this would be b2 minus 10 b1. Okay, now you can look at this thing that this rank of this matrix is 2. You have 2 sort of linearly independent. You can't further eliminate any row, right? So what kind of system this is? So in this system, you have to decide for more number of variables than number of equations. Okay. So in this kind of situation, what you have is, you have infinitely many solutions. Okay. So even in the assignment, if you row reduce this thing, sorry, this would be minus 5b1. Yeah. So in assignment also, if you, when you row reduce this matrix, that question is bit different. But when you row reduce this matrix and your second row don't turn out to be 0, then you can choose the option, the system has infinitely many solutions. Okay. Now let's say for some example, you would have obtained something different. Let's say after row reducing, the matrix that you obtained is 1, 2, 2, 0, 0, 0, and here you obtained the same thing, b2 minus 5b1. Then how many solutions we would have? Okay, so then the number of solution would depend on your values of b2 and b1. Let's say b2 is 1 and b1 is also 1. Then how would this matrix look like? This matrix would look like 1, 2, 2, 0, 0, 0. This would be 1. This would be minus 4. What does the second row imply? Second row implies that 0 is equal to minus 4. And that's obviously not possible, right? So if you encounter a matrix like this after row reduction, then what you need to ensure is that your this quantity is also 0. So this would mean b1, or this implies b2 is equal to 5b1. So for b2 is equal to 5b1, you will have infinitely many solutions again, and for other cases you will have no solution. Any doubt in this, whatever we discussed in this question? Okay. Okay. So now here the question is, you have to find the least square solution, whose formula I have already written. This is A transpose A inverse A transpose B, right? So we just need to calculate this thing. Okay, I have written, I guess. Yeah, here I have, right? So you just need to use this formula in this matrix. I want you to solve. It is 6:38. I'll wait till 6:41, and I would like to know the answer for this question. So A transpose would look something like 0, 1, 2, 1, 1, 1. You just need to multiply it with this matrix 0, 1. You will get something. It would be a 2 cross 2 matrix, and then you just need to find its inverse. Finding inverse of a 2 cross 2 matrix is very easy. Then you just need to carry some matrix multiplications. And if you look at A transpose B, this would look something like 0, 1, 2, 1, 6, 0, 0. Can somebody give me the answer? So if we look at this multiplication, this is 0, 1, 4, this is 5, this is just 1, 1, 1, 3, right? Sorry. And the second element would be, okay. Can somebody else also calculate and confirm? In the meanwhile, I'll calculate myself. 1 plus 2 would be 3, right? And this I have miswrote as 3. This would be 1 plus 2 again 3, which would be again 3. Okay, so what this would be? This would be 0, this would be 6. And what is its inverse? So you just swap the middle one and you take minus of that. Okay, and then you just multiply these two things, right? 3 minus 3 and 3, 5 divided by its determinant. What is its determinant? This is 15 minus 9, 6. This is 1 by 6, right? So you take 1 by 6, 0, 6. That would mean minus 3, 5. Yeah, third option is correct. So you have a very similar question in your assignment, and I have been asked to solve questions similar to your assignment, so I included this question. Okay. Okay. So we have one more question, right? The third option was correct. It was minus 3, 5. So now you are given a linear system. Ax is equal to b. Okay, and A is of order 4 cross 7. Then you have been asked about the number of free variables. Okay. Now assume that the rank of this matrix would be a minimum of 4 comma 7, right? That you need to assume to answer this question, because you can have a 4 cross 7 matrix in terms of size, but let's say you have only one independent row, then the answer would vary a lot. So in this case, let's assume that you have rank to be 4, rank of A is 4. Then you have been asked what is the number of free variables. Okay, so when you have what is the meaning of 4 cross 7? 4 cross 7 means you have 4 equations and you have 7 variables to solve for. Okay, so now again this comes to the concept of dimension of a subspace and those things that we talked. So if you have 7 variables and you have only 4 equations, that means that 4 of the you have 3 independent variables or 3 choices to make. Okay, so based on these 3 choices you will determine the value of other 4 variables. Okay, so it is 7 minus 4, that is 3 free variables. Okay, so the answer for this is 3. Okay. Okay, this is a slightly different question, but it would be interesting to do. This is not in your assignment, but it would be interesting to do. Now, let's say you are trying to find the, you are looking for some linear. Then it could have been, yeah, what is the minimum number of free? That's correct. Okay. So in this question, let's say you have this data set given with you. This is a small data set. Okay, and you have been asked to fit a linear curve to this data set. Okay, and by some sort of training, by something, a hook or a crook, you obtain this value for your theta, the value that this theta 0 and theta 1. Okay, you obtained this value of theta. Okay, you have been asked to calculate the mean square error for this case. Okay, you have been asked to calculate mean square error. Okay, how do we go about it? So you have x, you have y. Let's calculate h of x. Okay, so your x is 6, this is 7, 5, 4, 10, 9, and 3, 4. Now what is your x? X is, now theta 0 is 2, so this is 2 plus x. So what is your h of 6? This is 8. Let me use some other color pen. This is 8. This is 5 plus 4, 5 plus 2, 7. This is 12. This is 5. So what is the error that you get? The error that you would get is 1 square plus 3 square plus again 3 square plus 1 square. So this is 20 divided by 2 into number of data points. So this is 1, 2, 3, 4. This is 8. So the error that you would get is 20 by 16. So this is how error calculation works. So when you are applying, then generally your sklearn or some sort of gradient descent will do the calculations for you. But this is how error is calculated. So you have some h theta, then for some value you calculate this error, and then from there you move on to a point where you have lower error, and so on. You reach an optimal solution. Okay. Any doubt till now before we talk about regularization?
Sir, please repeat again this question.
So in this question, so if you recall, what we have been talking about is minimizing some error, right? When you do linear regression or those kind of things, you try to minimize some kind of error. In this question, you were given with a hypothesis function, right? So what was the hypothesis function? You are given with theta 2 comma 1. So h theta of x was 2 plus x. So the question indeed is, if your machine learning model learned that the function is 2 plus x, how much error are you making if your original data set is something like this? So we calculated h of x, and then we calculated the error based on the error formulation that they had given in the question. Was I clear this time?
Yes, sir.
Okay. Any other doubt before we go to regularization? Somebody has unmuted, but
Um, Sir,
mm-hmm.
how h of x become 2 plus x?
Okay. So how h of x becomes 2 plus x is that you were given that your h theta of x is theta naught plus theta 1x, and you are given the value of theta, which is 2 comma 1. So your theta naught becomes 2 and theta 1
Yes, sir.
becomes 1 into x.
Yes, I understand.
Rowan, do you have something to ask? Okay. No. We talked about two kind of problems. I didn't got your question though. So you are saying that the cost function is only 2m. Yeah, it's one of, yes, yes, I think. Yeah, so this would be 2 into 4, right? Not 2 into 8. I multiplied it in my brain and then sort of wrote it again over here. So this would be 2 into 4. Yeah. Okay. So yeah. So I talked about two kind of problems that you can face when you're training a machine learning model. One is underfitting and one is overfitting, right? So how do you get rid of underfitting? Getting rid of underfitting is very easy. You just increase your model complexity. So if you were searching within a space of linear classifiers or linear regression functions, then you start searching for quadratic or 3-degree polynomials. The underfitting problem would be solved, right? But the overfitting problem sort of requires some extra care. Okay. So one way to get rid of overfitting problem is something that is called as regularization. Okay. So before getting into regularization, I just want to include a very small thing. So we talked about, when we were talking about features, we had f1, f2. Okay. Then later on in example, we included f1 dot f2, sorry, f1 square, and then f2 dot f3. Okay. So now, if you look at your earlier feature matrix, it was A. Now, if your new feature matrix has become, let's say, a capital phi, then still you can find the minimum solution using the same formula, which is phi transpose phi, this inverse phi transpose B. Okay, still you can use the same formula. Even if you remove your earlier features completely and you transform your features into some new set of features, this is actually done via kernel functions. Okay, or other name for this is basis function. There are many type of basis functions that you can use to transform your features into nonlinear space, and you obtained a new version of your matrix, which is now let's say called phi. Then still this formula is valid. Okay, this was a very small point that I which point you didn't get?
Sir, this which are you explaining of removing some features?
Okay, so okay, I'll do this part again because this is sort of important. Now, Kushal, if you look at, let's say, you have a example where you have data points of something like this. Okay, so this is something like this. Your data points are something like this. But now you only know linear regression. Okay, and you want to use your linear regression to find a best fit line. Okay, so in this case, if you look, you have some x and you have some corresponding y. So if you look at feature, your feature only has only you have one feature, okay, which is your 1. This is f1, and you will have a bias term, right? You will have some bias term with it. So your how does a linear function looks like? This would look like let's say some alpha f1 plus b, right? This much I hope is clear. Okay, but if you look at, if you want to approximate this via linear line, no line is a great fit, right? But if you look carefully, if you approximate it with something like a quadratic kind of a curve, then that's a very good fit. Okay, so but you only know linear regression till now. You want to use whatever you have learned till linear regression to approximate this kind of quadratic curve. Now what I'm saying is, include an extra feature which is f1 square. Okay, now you will have to learn two parameters, right? This would be alpha f1 plus alpha 2 f1 square plus beta. Because you have already included this feature in squared form, you can now, if you rename, let's say this to be f2, now you have to only learn a linear regression in terms of f1, f2 and your bias term, right? So you can use this linear regression to approximate your nonlinear functions. Okay, now what I said earlier, that if you have some feature matrix A, then you can use this formula, right? This formula to obtain your best fit line. This is A transpose A inverse A transpose B. Okay. Now what I'm saying is, after you have included an extra feature, which is quite intuitive, even after adding, if you know if A was your earlier matrix, let's say this much was called A, Now after including this extra feature f2, you get a matrix phi. Then this formula is valid for phi also. That is, you can obtain the best fit line by phi transpose phi inverse phi transpose b. Okay. Now was I clear? Then I'll get to the second part that I talked. Kushal, am I clear till this point?
Sir, yes, you are clear, but the formula we had for linear kind of thing. So, but now we are applying in in phi matrix, which has a term, a square term also.
Right.
So that will not be an issue.
That won't be an issue because this is quadratic in terms of f1, right? But linear in terms of f2. So if you just rename this as f2, then doesn't it look exactly like a linear thing? So we have just
So
included some.
actually, we are changing
Mhm.
in terms of variable, but mathematically it is a square term.
That's why we are doing it. So we want to use a non-linear approximation, but the techniques that we are using is just for the linear case. Let's say,
Okay, so it's kind of approximation only.
so let's say you didn't knew that somebody is squaring, and somebody like before presenting the data to you, somebody already did this f1 square and included it over here. Then it is then you would think that it is linear. The same way the linear regression thinks that this is a linear approximation that that person is doing, because we are presenting them already a squared term. Okay. Now after this point, what I told was there are many motivating examples, or there are many functions called as basis function or kernel functions. Okay. uh, you can if you are applying it in a more complex data, or yeah, when you apply for more complex data, what you can do is you can transform this your features f1 f2 f3 into some features like phi1 phi2 phi3, which are sort of very different. Okay, so something like you take sine of f1 and you remove f1 now. Okay, and you obtain something known as phi1. Okay, and you take, let's say, 1 upon 1 plus e to the power minus x, this f2, and you obtain f3 f2 phi2, sorry. Okay, so you obtain a completely new set of features. Okay, now if you apply the same formula on your new set of features, then still it's valid. That's what I was saying. Okay, so you can have a look at basis function or kernel function. Okay, so yeah, so this is what I was telling. Okay, now let's get to regularization. Okay, so one thing that I think should have been clear from my this whatever we have discussed in an hour is, let's say when we do a linear regression, or this whatever I'm talking about regularization is true for any sort of machine learning algorithm, not only regression but also for classification, even for deep neural networks. This thing is valid. Okay, so when we talked about linear regression, what we did was we were trying to minimize some loss or error. Okay. Okay, so what was this loss? This was something like f of x minus y. Okay, subject to what? Subject to think that my f should be linear. So if you think about it, so when we say that that we are finding the best fit line, isn't this the same thing, that if my f is linear and it is minimizing the loss, then that's what means that it is the best fit line. Okay, so now, so you can extend this thing to something like minimize, okay, f of x minus y such that f belongs to some let's say class of function called h. Okay, some arbitrary set of functions you have, you want to search over that space. Okay, that can be set of linear functions, that can be set of quadratic functions, or some variants of it. Okay, now what is the idea of regularization is, regularization says that rather than searching all linear functions, what you do is you search linear functions only whose uh, this constant terms in those. So for example, if you have a linear function like ax plus b, a and b are your constant terms in your this linear function. So your constant terms are very close to 0. So you only search for those linear functions such that your constant terms are close to 0. Okay, so they are as close to 0 as they can be. Okay, now this regularization is a method to tackle overfitting. Okay, okay, so let's look at this example. Let's say in this case uh, you had this point, this point, this point, this point, and yeah, okay, and this red line was very well able to fit to this particular data set. Okay, now again you say that you made an error in calculating this particular point. Okay, and you predicted that point to be this point. Okay, now if you look at the new line, this would be something like this, then here, then here, then here, and later on it will go on. Okay, so you have very large values, and if you look at the difference between these two functions, this is very large. So the error that you will make because of the noise is very high. Okay, whereas if you had smaller coefficients, so this red line had larger coefficients, right? 5x cube minus 5x square minus 5x plus 5, and this is same sort of thing with a lower coefficient. Now even this was not a very good fit for the data set that was presented. Okay, but now because of error there won't be much change in the function. This would be something like this. So the change that you are observing is not very high. Okay, so this is sort of very close to your testing data set, whatever you could have obtained on the testing set, because this is not making a lot of difference because of just some small noise. Okay, so this function sort of have become stable. So this is the idea behind regularization, that whatever functions that you are searching over, in those functions you don't want very sharp changes. So if you have higher coefficients, then you will have very sharp changes in the function, whereas if you have lower coefficient, your functions will like change its direction very slowly. Okay, so this is what is known as regularization. Okay, so what do we do in regularization? So if you remember what we were doing, we were minimizing this f of x minus y. Now with this thing you include an extra term that you want to minimize, which is, so if your fx was, let's say, ax plus b, then this lambda would include some mod a plus mod b. Okay, this norm can change, right? If you write this a b as a vector, let's call it w, then instead of this ab you can have any norm. Okay, you can have 2 norm or p norm based on whatever we did last time. Okay, so right now I have taken one norm over here. So if you now minimize this whole term rather than just minimizing this part, what you are forcing is that your value of a and b should also be as close to 0 as possible. Okay, so this is the idea of regularization, and when you try to implement in your codes, you just need to include this extra term in your loss function, and then whatever you are using, either sklearn or your gradient descent thing, that will take care of everything after that. Okay, Okay. So this was about regularization. Any doubts in regularization? So
Sir, can you
regularization
scroll up to basis part?
basis part, basis function and kernel function.
Yes, sir.
Okay.
Sir, in this case, we have changed from F to 5. So we
Yeah.
have kept F as a basis matrix,
Okay.
basis functions.
So basis functions are these is a name for these kind of functions. So sine f1. So neither f1 or phi1 is basis, but the function that you use to get from phi1 to this f1 to phi1, those are called basis functions. It's just a nomenclature. Okay.
Okay,
They are
sir.
also called as kernel functions. So kernel functions can so these both these basis function as well as kernel function can also take more than one feature to produce other function, other this feature phi1 or those kind of things. Okay. Okay. So I'll come to bias and variance. Just before that, we'll talk about these two terms, which is called as ridge regression and lasso regression. Okay. So now we will generalize our notation a bit. Okay. So what we are doing, we are minimizing f of x minus y. Okay. And this f belongs to some set of functions. This can be linear or whatever you want in your application. Okay. And this f, let's say if it is ax plus b, or let's say it is a1x plus a2x2 plus b, then we are writing its coefficient in a vector called w. Okay, so w is either ab or it is a1 a2 b. Okay, so now that vector we are calling as w. Now when we talked about regularization, what we said is we will include an extra term with w norm. Okay, now this ridge regression is nothing, I am telling you it's nothing but a fancy name for linear regression when you include your this regularization term with L2 norm. Okay, so linear regression was minimizing f belong to h, f of x minus y, and your ridge regression is minimizing this plus lambda times of L2 norm of w. So L2 norm is nothing but your Euclidean norm, that is under root of w1 square plus w2 square and so on. For in this case, this is under root of a1 square plus b1 square, a1 square plus a square plus b square. Okay. So if you just take two norm for your regularization thing, this thing is called ridge regression. Okay. And what is lasso regression? Lasso regression is when you take your regularization term with L1 norm. So rather than this, if you had just this as L1 norm, that particular thing is called lasso regression. Okay. So in lasso regression, there is a property that you sort of get sparse features, and in ridge regression that is not the case. Okay. But in from application point of view, or when you will sort of apply in real life, 90% of the time or 95% of the time you would be using ridge regression only. Okay, you will be taking L2 norm for the this regularization parameter. Okay, so now this thing was not there in lecture. I thought I should include it. Okay, now we talked about all kind of variants. When we had A transform to phi, the formula still holds A transpose A inverse A transpose B. Okay. Now if you have included ridge regression, that is you have included W2 norm, then you can just modify that formula to this formula. Now your formula becomes A transpose A plus lambda times I inverse A transpose, this is again transpose, okay, B. So you just included an extra lambda I term, okay. So yeah, this is just what you need to do when you apply Ries regression, okay. And one more thing that I just want to point out over here is when you have your A transpose A, you used to write that A transpose A inverse A transpose B. It is not always necessary that your A transpose A inverse exists. In fact, in many cases, even though the data set is very random, but there would be some case where you would encounter that your A transpose A inverse don't exist. Recently, I was working on a data set, some graph data set, and there also I encountered that A transpose A inverse was not invertible. Okay, so there was something similar matrix which was not invertible in the loss function. Okay, so so if you use even a very small regularization parameter, if you take very small lambda also, let's say you take 10 to the power minus 10, okay, you take very small lambda. Now this matrix that you obtain after regularization thing, this thing is always invertible. In fact, this turns out to be positive semi-definite, and that's why it turned out to be invertible. Okay. If you want to prove, you can even prove that this is positive semi-definite. So what is positive semi-definite? X is positive semi-definite if your V transpose XV is greater than equal to 0, right? This is what is meant by positive semi-definite. So if you apply it here, so this would be V transpose A V plus lambda times V transpose I V. Okay, so what is this? This is just V transpose A transpose into V transpose A transpose transpose, right? Plus this is lambda times norm of V. This is V transpose V is norm of V, and this is norm of V transpose A transpose plus lambda times norm of V transpose. So both are norms, so sum of norm is always greater than equal to 0. That's why this matrix would always be invertible. Okay. 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 Now in this discussion, you might have seen one thing. We'll get to bias and variance very soon. That there is this guy called lambda, right? So even when you are writing lambda omega 2, then the question comes is, what is this lambda and how to calculate this, or how to get to know about this lambda? Okay, so this lambda is called as regularization parameter. Okay, so this lambda in fact is not explicitly known to us. Okay, so how do we calculate this lambda? This is treated as an hyperparameter. Anybody knows what is an hyperparameter? I think most of you would, but anyway, so I would ask the other way around. Do you know what is an hyper? Anybody over here who don't know what is an hyperparameter?
Yes, sir.
Okay. So in machine learning models, there are some parameters that you solve via training, okay, or you obtain via some method or other, okay. There are some parameters that you actually don't solve, and those are called hyperparameters. You check different values of those parameters and end at the point choosing the best one whatever you have obtained. For example, if you have this lambda, you can train let's say you will have to train let's say 4 or 5 models, once with value let's say 0.1, once with 0.01, and so on. Okay, and then whatever accuracies that you are getting, you can pick the best one out of these lambdas. So these kind of parameters are called hyperparameter. Okay. So again, the accuracy that you should check should not be on your learning data set. Okay. Or the training data set. It shouldn't be on the training data set. So in machine learning, what general practice is, if you have a data set, you split your data set into 3 parts. Okay. First one is called training data, and you should keep something around 70 to 80% of your data set as your training data set. The second part is called as your validation data set, that you can keep as 10%, and third one you can keep as your test final data set. Okay, that you can keep as 10%. Okay, now you train on the 70%, and for choosing your hyperparameter, you test the performance or the accuracy of your model on validation data set. Okay, and based on that validation accuracy that you are getting, you choose your best hyperparameter. Let's say 0.001 turned out to be your best hyperparameter. Now with this best hyperparameter, you again run your experiment on test data set, and this is the accuracy that you should report to the world, that I am this much accurate on some unseen data set. Okay, this is how this thing works. Was I clear with hyperparameter and how to tune it? Whoever said that she didn't know about
Yes, sir.
hyperparameter. Okay. Okay. So this was about hyperparameter tuning. Now we should go
Sir,
to, yeah.
I have one question. What is in the fair solution?
What is meant by
Fair solution.
fair solution?
Huh.
So
Which was in assignment, which is related to ridge or loss regression.
just a second, let me have a look at the question, then I can better answer. Give me a second.
आणि हात
Which question are you referring to? Okay. I don't see a term called. Okay, is it sparse solution that you are talking about? Can you type it in the chat box? Is it sparse that you are saying?
Yes, sir. Yes, sir.
Okay. So what is meant by sparse is, so when you train a model, what do you get? You get some weights, right? Or if you talk in terms of linear regression, you get value of A and B. Okay. So if you have higher order models, then you will get some A1, A2, A and B. Okay. What does sparse solution mean is that like many of these A1, A2 or ANs that you would be getting, that would be 0. Only some of them will be non-zero. Okay. So this is a property of your lasso regression, that in case of lasso regression, you get a sparse solution where many of your features are have 0 weights. Okay. And in case of ridge regression, the solution is not sparse. Okay. This I think I mentioned few moments ago. Okay. Yeah. Okay, we will go to bias and variance.
Sir,
Yeah.
so where you were explaining about the validation and test data, the
Mm-hmm.
final value which come after applying on test data is our lambda.
No, 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 no. Okay. So based on validation data, for whatever value of lambda, you got the best accuracy. Accuracy is the opposite of error. Okay. So I'll just include one more thing over here. So now you trained on a training data set. How did you train? You looked at the error between fx minus y. Okay. Now also on the validation set, you will look the error between fx and y. But now the input x will change. Earlier you were looking for all the x that belongs to training data set. Now you will look at all the x's that is for your validation data set. The lambda that you will choose will be the one that gives you least error on your validation set or the maximum accuracy. Okay. Now you have fixed your lambda. The role of testing data is just to test your model to report it to real world. Okay, let's say you trained some model and you want to present it in a meet. Let's say you have a client or some company for whom you are modeling. Okay, then this test data will only be used for reporting that I have got this much accuracy for my model. Okay, because you are fitting your data, your model to training data set and fitting your lambda according to your validation data set. That's why you should always show or present accuracy to the real world based on some unseen data set. That's why we keep some small test data set. Was I clear? If I'm not clear, please ask me again. I'll try to again explain this part.
Sir, this validation part. First, we find the minimum error for all the x in training data set, and then for the x we get the least value. We put that into validation data.
देखो, I'll sort of write in steps. अगर फिर भी नहीं समझ आए तो प्लीज वहीं पे रोक देना मेरे को जहाँ पे नहीं है, ठीक है. So first of all we have some data points xi yi, ठीक है. So let's say we have 100 of these data points. We have x1 y1 till x100 to y100. What we did is we took x1 to x80 y80. This much we took as training data. Okay. अब x81 से till the point x90 and y90 we took as validation. Okay. Now let's say x91 to y91 to x100 y100, we are keeping it as test data. Okay. The first step is to train your model. Okay. What we will do is, what is the goal of training? We have to minimize the loss, that is sum from 1 to 80, क्योंकि right now we are working just with training data. This would be f of xi minus yi mod plus lambda times w. Okay. Now question is, what lambda should we keep here? Okay, in training what lambda should we keep here? So what you will do is, for the first time, let's say we took lambda to be 0.1 and we trained the model. Okay, what we will get from training? We will get f from training. है ना? What we will get? We will get parameters of this f, which is w is equal to a comma b from training. Is this much clear what we will get from training after we have fixed our lambda?
Yes, sir.
Okay, so we will get some w. Now using this same function, we will calculate loss of validation set. ठीक है. अब अगर एक बारी हमारे पास f आ गया तो we can put f of x81 and take its difference with let's say f of y of 81. ठीक है. And we can take their sum, right? 81 से लेके 91 तक we can calculate the validation loss. This is the validation loss. If I take I from 81 to 91, this is exactly my validation loss. ठीक है. Now we did it for one lambda, that was 0.1. Now we will repeat this process again. Let's say this is loss validation at 0.1. We will repeat this process again for lambda value 0.01. Okay, and we will obtain some loss of validation 0.01. ठीक है. Now among the set of this validation loss you are getting, let's say this, and you will get bunch of them more, you will choose the one with minimum loss. So this we are doing to find out lambda. So we use training data to find out f, right? And we are using validation to find out our hyperparameter, that is lambda. Based on the minimum, whichever lambda gave me minimum value, I will take that particular lambda. Okay. Now after you are done with all of this, you will be only left with one function. Okay. So the function that is obtained by this best lambda. So let's say you have some a star and b star corresponding to this. This is this optimal weight. Now using this optimal function, this is the best function that you could have got. You will calculate the loss on your test data, that is I from 91 to 100. You will calculate f of xi minus yi. Okay. And this loss you should report to world, that this my model is giving this much error, or if you just take the opposite of it, that is 1 minus the error, okay, then you can tell that my model is giving me this much accuracy. Okay. Report to the world. Was I clear now?
Yes, sir. Now it is clear.
Okay, thank you. Okay. Okay. Now we will talk about two terms that is associated with this concept of overfitting and underfitting. Okay. This is just giving names to what we have already talked about. Okay. So there are two terms. One is called bias and one is called variance. And there is a famous quote associated with it. This is called as bias variance trade-off. Okay. So now what is bias? Bias is, okay, so if you have, let's say, okay, I'll try to motivate it slightly differently. This can be slightly not very intuitive, but I'll try to motivate this thing in this way only. This I think is the best way. Not here. Just give me a second. This is a recommender system, not even here. Okay, yeah. So this is from my earlier course that I used to do. This is Introduction to Machine Learning by Professor Sudeshna Sarkar from IIT Kharagpur. Okay, I prepared these notes then. I'll use this to explain what is bias and variance. Okay. Now, let's say yeah, let's say what you actually just slightly try to listen to me, and if you have any doubt, just stop me. Let's say you know that in real world, actually your data is obtained from this particular curve. Okay, right? Your data is obtained from this particular curve. Okay, but you don't have access to this curve. Okay, you in reality don't know that what is this curve, but you only have some samples from that curve. Okay, you have, let's say, this point. Okay, and you have this point with some noise. Okay, there will be some added noise by capturing some data points from this curve. Okay, now you want to approximate this curve. Okay, now in this example we are trying to approximate it via a linear function. Okay, this is via some linear function. So now you approximated this particular thing via a linear function. Okay, now let's say you took another sample of some 20 points. Okay, let's say those points were something like you obtained a point from here, 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 here. Okay. Now for these, so one set of points you earlier obtained this line. Now using these pink lines, you obtain some another line. Okay. So now in this next figure, what is done is we have taken 50 such samples. Okay. So once we sampled from that particular this curve, and based on the points that we obtained a linear regression. Now again we sampled, we again obtained a linear regression. So we have 50 different lines that fit to this particular curve, that we are trying to fit to this particular curve. Now what is bias? Bias is if you take average of these lines that you have obtained. Okay, all these 50 lines that we have obtained, if you take the mean value or the average of that thing, you want to see how far this mean curve is from your actual curve. Okay. So if you want to try, if you try to capture this thing, that thing is called bias of your model. Okay. Now just think this way. If you approximated this thing via linear curves, right? Let's say this case 1, when you approximated via linear curve, and in case 2, you approximated via quadratic functions. So if you took many quadratic functions and then took their mean, then that would have been much closer to this actual curve, right? So there the bias would have been less. So if you increase the complexity of your model, your bias decreases because now the average values will try to get closer to this original function. Okay. So if you try to plot, let's say, this is your model complexity and this is your bias. So if you plot bias, as your model complexity grows, your bias is decreasing. Okay. And if your bias is high, what does this mean? When your bias is high, that means your function is whatever class you are searching your function is, that is not very good, and that's why you are not able to approximate it very well, and your data is underfitting. Okay. Now there is another term which is called as variance. What is variance? If you look at these 50 examples and you calculate the variance of these data sets, what is meant by variance? Variance is that how far are these from each other. Okay, that is something that is called as variance. Okay, now if you recall the example where I talked about if you just change one particular point, let's say you changed this point to here, then the model would look something like this, right? Not a very great example. Okay, let's say that you change this point to this. So beyond this point, it would be something like this. So there is a large variation in the functions just because of very small perturbations. Okay. So for when your model is very complex, okay, as the model complexity increases, your variance increases, because as the model is complexity is increasing, your model is trying to fit very close to your training data points. Okay, so this reason corresponds to overfitting. Okay, so what is the range in which you should look for a possible class of functions in which you want to search? You should look something in this region. Okay, so there is no best class to look in, but people generally look in this region where this bias and variance thing kind of crosses. Okay, so if your bias, you can just remember this thing, if your bias is high, that means you are underfitting. Okay, and if your variance is high, that means you are overfitting. So you want a sweet spot, so that's why you choose something on the intersection of both these curves. Was I clear in explaining this thing, this bias and variance thing?
सर तो वेरिएंस में तो हम यही कैलकुलेट करते हैं ना कि हमारा जो पॉइंट है वो मीन से कितना दूर है, मीन से कितना डेविएट हो रहा है एक तरीके से।
हाँ 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 बिल्कुल।
तो फिर वो हमारा जो मेन कर्व है वो एक्चुअल पॉइंट से ज्यादा डेविएट कैसे हो रहा है, ये समझ नहीं आया।
अच्छा, मतलब अगर हमारा मॉडल कॉम्प्लेक्सिटी ज्यादा है तो एक्चुअल पॉइंट से कैसे ज्यादा डेविएट होगा, ये ना?
यस सर।
ठीक है, मैं कोशिश करता हूँ। तो देखो, एग्जाम्पल वही वाला आएगा बार बार, क्योंकि देखो अगर क्या होगा, लेट्स से you have, I'll try to draw three different curves. ठीक है, कुछ ऐसा है। तो इनिशियली तुमने ऐसे फिट किया, ठीक है, ठीक। अब तुमने दोबारा जब सैंपलिंग की तो पता चला तुम्हें कि ये पॉइंट यहाँ नहीं है, यहाँ आ गया मान लो, ठीक है। तो अब क्या किया तुमने कि ये पूरी लाइन तो ऐसे ही रही, यहाँ से ऐसे जाके ऐसे हो गया। अब अगर एवरेज निकाले हम लोग इन दोनों का तो कैसा दिखेगा, इधर से सेम और यहाँ से कुछ ऐसा, ठीक है, समथिंग लाइक दिस। और फिर यहाँ से तो ऐसा ही आ जाएगा, ये बीच में दिस वुड बी समथिंग लाइक दिस, ठीक है। अब इसका मीन से देखो कितना डेविएशन है, क्योंकि हम लोग बहुत अच्छे से फिट करने की कोशिश कर रहे हैं तो कुछ डेविएशन है। अब सेम एग्जांपल लेते हैं, ठीक है, और एक थोड़ा कम कॉम्प्लेक्सिटी का फंक्शन हम लोग इसमें वो करने की कोशिश करेंगे। यहाँ था, यहाँ, ठीक है। अब हमें लीनियर लाइन इसमें फिट करनी है, तो लीनियर लाइन थोड़ी बहुत कैसी दिखेगी, ऐसी दिखनी चाहिए, ठीक है। नाउ लेट्स से वी शिफ्ट दिस पॉइंट टू दिस पॉइंट, उससे कैसा चेंज आएगा इसमें, सो दिस वुड स्लाइटली शिफ्ट डाउनवर्ड्स, ओके। तो अगर मीन लाइन देखो तो ओवरऑल हर पॉइंट पे जो वैल्यू में तुम्हारा वो आ रहा है चेंज, बिकॉज वी हैड नॉइज ओवर हियर ओनली, so you need to see the variance at this particular point, okay। तो कितना variance है, if you had smaller complexity model then the variation is very less, but when you had larger complexity model तो वहां पे एक छोटा सा शिफ्ट करने से भी पूरे स्ट्रक्चर में काफी चेंज आ जाता है, दैट्स व्हाई योर वेरिएंस विल बी हाई। क्लियर हुआ क्या अब?
यस सर।
ओके, okay, now we'll get back to what we were doing. So this was the story about bias and variance, okay, okay. So we have some 20 minutes left, so I'll go, yeah, I have to do this logistic regression. So we talked till now about the task of regression, okay. The second thing is classification, okay. Now I'll just tell you the idea of sigmoid function. What does this sigmoid function do? If you plot this sigmoid function, you don't plot this sigmoid function, you just look at the values that you will obtain, okay. What is s of 0? S of 0 would be half, right? What is if you take x towards minus infinity, what is this value that you are going to obtain? So this thing going to minus infinity, that means that minus x is going towards plus infinity. So 1 upon 1 plus e to the power infinity. So this value will be very high. So the denominator is very high. So my s of x should tend to 0. Okay. Now if my x is going towards infinity, then s of x will tend to 1, because this term will tend to 0 and overall this term tend to 1. Okay. So in classification, let's say you have two classes. Okay. You have 0 class and you have 1 class, and you want to classify your points in these two classes. Okay. So logistic regression name says that this is a regression because the idea is based on regression, but actually this is a classification technique. Okay. It uses regression to do classification. You can say something like that. Okay. So how does this do classification? The idea is same. Let's say you have some data points. Okay. So let's say you have these are 0 class data points, and let's say we mark by, let's mark them by star. So these are some let's say plus these are 1 class data points. Okay. So what is the idea behind logistic regression? What does logistic regression want to do? Logistic regression wants to find a line such that on one side of it, all the points are of one type. On the other side, all the points are of other type. Okay. Now, if you look at this line and this is the perpendicular to this line, then one thing that you should know is that if you take, let's say this perpendicular is, let's say W1, W2, okay, and if you have any point that you take from here, x1, x2, let's say, so this is the direction of perpendicular. So every line will have a positive normal and a negative normal, right? So this is the positive normal direction. So if you take its dot product with your x, then you will get a value greater than equal to 0. So, and on the other side of the line, if you take any point, if you take W transpose x, you will get value less than equal to 0. So you can, you should know this mathematically, that for a line, if you look at this W, okay, then on one side you will get all the points whose W transpose x is greater than 0, and you will get a line, so on the other side W transpose x is less than equal to 0. So what we want to do is, we want to find this particular line, which means we want to find this W1 and W2, because if we find the line, this W1 and W2, we can draw the perpendicular and we know what the line is, right? So we want to find this W1 and W2 so that for all the points on this upper side, this thing should give us greater than equal to 0, and on the lower side this should give us less than equal to 0. Okay. Now how do you want to do the training? Now what we want to do is, if anything is greater than equal to 0, I want to map it to something that is close to 1. Okay. So if you look at sigmoid function, when we have values greater than equal to 0, what is the value that we will get? We will get, so I'll plot this sigmoid function. This looks something like this. Okay. S kind of a curve. Okay. And this is, let's say 0 point where you get half value. Okay. So now if my x is greater than equal to 0, what values I am getting out of s of x? So s of x is close to 0. So if I do s of W transpose x, if this is close to 1, that means my point are on upper side of this line, and if it is close to 0, that means the point are on other side of this line. Okay. So how do we go about training of this thing is, now for every point here you will have xi and some corresponding label, either it would be 1 or it would be 0. Okay. So it would be 0. So what you would do is, you will define a loss function such that that your loss is defined as error between your yi, okay, your yi minus s of W transpose x. So earlier, if you remember, we used to define loss between yi minus W transpose x directly, right? But now what we will do is, we will first pass this W transpose X through this sigmoid function and then calculate the error. Okay, and then again we will do all those minimization thing to obtain our answer. So this is about two-class classification using logistic regression. Okay, any doubts in this before I go to multi-class?
So the W's are the length of perpendiculars.
W is the vector perpendicular to this. This won't be length, but the direction.
Yes, sir.
जैसे if you look at this thing, एक axis बनाते हैं 2 dimension में, ठीक है? So what is this line? This is x-axis line. So if you draw a perpendicular, what is this direction? इसको let's say we denote it by unit vector only. तो ये direction क्या हो जाएगा? 0,1. Okay. So similarly, if you take this line x is equal to y, what would be this direction? This would be, I guess, this is half of na, so this should be 1 by root and 1 by root 2. Okay. So similarly, we can define. यहाँ पे sign का थोड़ा वो हो सकता है. So our task is to find that thing, right? So with W you can so this W is such that W transpose X is equal to 0. So this should be a minus half. Okay. So equation of line is W1 x1 plus W2 x2 is equal to 0. तो ये हमारी लाइन की इक्वेशन है, इस वाले लाइन की इक्वेशन. So if you write its coefficient together, then you obtain the W. Okay, so I'm slightly hurrying up, but I thought I would cover more content that might be useful to you. So अभी हमने क्या किया कि we are able to learn a W which can classify or differentiate between two classes. Okay, but if you look at the real world data set, then it's very rare that you will come across this binary or two class data set. Generally it will have more than two classes. For example, if you look at a data like Amazon data set, where you classify every item based on the type of item it is. For example, whether it is an electronic item, whether it is a cloth, whether it is a grocery. So you will have multiple classes, right? So there would be very rare cases where you will have only two classes. But whatever we learned right now was only for two classes. Okay. So how do we tackle more than two classes? That's what we are going to come to. Okay. So if you have more than two classes, there are two possibilities. One of them is called multi-class and another is called multi-label. Okay. Now I gave you an example of this Amazon data. There, if you look, if you have, let's say, this mobile phone, okay, then this mobile phone can only belong to electronics category. This cannot belong to cloth category, right? So every point have only one label. Okay. Now consider another example. Let's say you want to there are what are your labels? Labels are the subjects that a student studies in his school. Okay, English, Hindi, maths, these kind of subjects are the labels that you want to assign, and items are people or the students. Okay, now every student will obviously not only study mathematics, right? There would be combination where the student is studying mathematics plus let's say physics plus chemistry. So every student will be labeled more than one label. So every person will be assigned more than one label. Okay. So this kind of setup is called as multi-label classification. And where you had only one label being assigned, that is called as multi-class classification. Okay. This was a certain, okay. So how do you deal when you have this more than two classes, either in case of multi-label or multi-class? One method that you can use on top of your logistic regression is called as one versus rest method. Okay. So what is one versus rest method is, let's say you have three classes. Okay. One is red, blue, and green. In this method, what you do is and you have some data set associated with it. Let's call it D. Okay. Now, what you do is, let's say data points which are red, you name it DR, which is blue, you name it DB, you call it DG. You create 3 new data sets. Okay. One is D1. Okay. What you do in D1, you take DR as red and you take DB union DG as not red. So using D1, you can train a logistic regression which can tell you whether that data point is red or not red. It can't tell you whether it is blue or green, but it can tell you that it is not red. Okay. Now you train another model, which is your DB blue and DR union DG, which is not blue. Now you have two models, right? One which can tell you whether it is red or not, and another which can tell you whether it is blue or not. Okay. Now using both of these combinations, right, you can tell whether a point is red, blue or green. Okay. So if you have some new sample, you will first check whether it is red or not. If it is red, it is well and good. If it is not red, then you send it to the other model and check whether it is blue or not. If it is blue, you assign it label blue. If it is not blue, then you will assign it as label green, right? So if you have again multi-class, then two models would be sufficient. Now, if you want to assign more than one label to every data point, then you also need to create a third model which will have DG as green, and you will have another partition where you have DG union DR, which will tell you not green. So in case of multi-label class, this data set, what you will do is, you will pass it through every data set. Based on first one, you will decide whether it is red or not. Based on second, you will decide whether it is blue or not. And based on third, you will decide whether it is green or not. Okay. Was I clear till this point?
Yes, sir.
Okay. Now there is one more technique that is more common actually, which is called, so this sort of requires your deep learning models, or even if not deep learning models, when you look at our regression or classification model, what we used to do is we used to map this, we used to find this f, right? What was this f? F was generally a function from feature space to real number. Okay. Now, rather than giving one real number, if you map this to some Rn, where n is your number of classes or number of different type of labels that you can have, then based on those k outputs, you can use some softmax function. Okay. So I won't go into detail, I'm just mentioning it because if some of you later on maybe encounter this kind of problem in real life, then at least you can look at these terms and you can have a solution. Okay. So in deep learning, this kind of things becomes very easy where you output k values rather than just one value. And then on top of it, you use softmax to convert these k values into k probabilities. Okay. Now, based on this probability, whichever has maximum probability, you can say that my data point belongs to this particular thing. So using this method, you will have to train very less number of models. So let's say if you had 10 labels, then here you had to train 10 different models. But in this case, you will have to train only one model. Okay. Now I'll go to important part, so which is called gradient descent method. Okay. So yeah. So I have been telling you that we will minimize this function. Okay. Minus y, but I didn't tell you how will we minimize this particular function. Okay. So the most used type of minimizing technique that we do use these days is something that is called as gradient descent method. Okay. So like whoever has done a basic course on calculus, he would know that if you have a function, okay, which is a function of, let's say, x1, x2, xn, okay, if you take its gradient, that is the direction in which your function increases maximum. Okay, so now if you look at this error, error is also a function of your weights. Okay, based on weight that you give, it tells you the error that you will have on your training data set. Okay, so this weight is not a single value but a vector, right? W1, W2, Wn. Okay, so now if you calculate the gradient of this error, okay, that will give you the direction in which the error is increasing maximum. Okay, now what you will do is you want to go in the opposite direction of the gradient so that your error decreases maximum in that direction. Okay, so for example, if you wanted to minimize a and b, then you will go from a in direction in which your derivative with respect to a, so this gradient is given by del E by del A. So you will move in opposite direction of your derivative. Okay. So this is how gradient descent works. So you will just need to calculate the partial derivative of this error function with respect to every of your weights and then move in opposite direction, right? Now this alpha tells you how much you should move in the opposite direction. Okay. So again, this alpha, how to choose. So if you, let's say you were at this particular point, this is, let's say, some error, and you chose a large alpha, you came to this point, then you came to this point, and your step length was big, so you came here, then again you came here and you jumped out. Rather than hitting this point, you jumped out. Okay, now let's say your lambda is very small, sorry, alpha is very small, then you will take very small steps, right? You will reach here, then reach here, then reach here, then reach here, and you will take very long time to converge. Okay, so we try to again hyperparameter tune this lambda, but this time we don't use our validation set, but we will see how our loss function is decreasing. So what you can do is after every iteration, you can iteration means that you have calculated the gradient and then moved in opposite direction of the gradient. You keep checking or you keep printing the error on the training set that you are making. As long as you are going down, that means that your error is decreasing, you are okay, you stick with that alpha. If you see that you are moving very slowly, then what you can do is you can increase your alpha slightly and then try retraining it. But in case you see that your error was decreasing and suddenly it started increasing, then in that case what you can do is you can choose a smaller value of alpha. Okay, so yeah, this was about gradient descent. There are a couple of more terminologies related to gradient descent. Okay, so now if you remember the example that I gave, that how do you calculate the loss, this is I is equal to 1. Let's say there were 80 points in the training data set, then this is f of xi minus yi. So this is your error. Okay, if you take its gradient, let's say del E by del W1, then this would be something like summation of I is equal to 1 to 80 del of this term, this norm, by del W1, right? And this would be sum over all these 80 training points, right? Now, in reality, you have millions and billions of data points in some examples. And if you keep calculating this gradient over all the data points and keep adding them and then move, the process can be very slow and compute heavy. Okay, so what people have suggested is, rather than calculating the gradient for complete data set at once, what we can do is we can just calculate this gradient for, let's say, first data point. Okay, and move in this direction according to the first data point. Then we go to the second data point, and then we calculate the gradient at second data point, and then move according to that. So if we, rather than taking this sum and then moving at once, if we just take one point and keep moving, this method is something that is called as stochastic gradient descent, or SGD in short form. Okay, so in this kind of thing, you update based on one data point at a time. Okay, so this process can be a bit erroneous because we are using only one data point. So you might be wondering a little bit. So if you look at this kind of curve, so rather than coming smoothly down here, what SGD can do is SGD can go slightly here and then come back, then here and then come back, then slightly go up. So this is sort of random walk kind of thing that it might do. Okay, so to avoid this kind of setup, what people have suggested is, okay, you don't go for the complete data set, you don't go for the one single data set. What you can do is you can go for mini batches. Let's say you go for sum of 10 data points. Okay, if you have 80 training point data points, then you can go 8 times in batches of 10 10 10. Okay, so this is something that is called as mini batch gradient descent. Okay, so I think the time for today is up. Anybody has any doubt related to this gradient descent? I'll stop.